Hello guys, today we're gonna do AP Chemistry 2021 FRQ1 today. So let's start. As you can see, we have an equation. We have the equation for the ionization of methonic acid, HCOOH. And we know the Ka is equal to 1.8 times 10 to negative 4 power. So part A, we need to write expression for the equilibrium constant Ka for the reaction. So that's pretty easy. Right? Ka is equal to the concentration of hydronium ions, H3O plus, times the concentration of HCOO minus divided by the concentration of HCOOH. All right, that's easy. Part B, we need to calculate the pH of 0.25 moles per liter solution of HCOOH. So firstly, in order to calculate pH, we need to know what's the concentration of hydronium ions or hydrogen ions is. So we need to set up an ice box or ice table. All right. So ICE, we have three different chemicals. We have HCOOH, H3O plus, and HCOO minus. At first, we have 0.025 moles per liter of HCOOH. We have no H3O plus and HCOO minus. In the reaction, X has been consumed, or HCO has been consumed, and X moles per liter of H3O plus have been produced, which means X of moles per liter of HCOO minus has been produced. So in the equilibrium, we have 0.25 minus X moles per liter and X moles per liter of H3O plus and X moles per liter of HCOO minus. So let's set up plugging this result back into Ka, the equation for Ka. So we have X times X, which is X squared, divided by 0.25 minus X. And that is equal to 1.8 times 10 to negative fourth power. Let's rearrange the equation first. By rearranging the equation, we times 0.25 minus X on both sides. So it becomes 1.8 times 10 to negative fourth power times 0.25 minus 1.8 times 10 to negative fourth power times X. We move this to the left side. So the equation becomes X squared plus 1.8 times 10 to negative fourth power X minus 1.8 times 10 to negative fourth power and 0.25 equals 0. All right, so now we need to use our calculator now. We need to plug in the value into the calculator. We go to apps, go to poly SMLT2, and we go to polynomial root finder. We choose next. Remember the word should be 2 because it's quadratic equation. So we choose should be next. Okay, so the coefficient for x squared is 1, so just 1, and we have plus. This is plus, and we have 1.8 times 10 to negative fourth power for a coefficient of x. 1.8 times 10 to negative fourth power. And for the next one, the sign for the coefficient of the constant for the constant is negative, so it should be put negative minus, and then the constant is 1.8 times 10 to negative 4 times 0.25, so it's 1.8 times 10 to negative 4 times 0.25. Click solve, and the final answer is for x is 0.0066. So if x is equal to 0.0066 moles per liter. Now we know this is equal to the concentration of hydronium ion, which means the pH is equal to negative log of x, which is equal to negative log of 0.0066. So pH is equal to, plugging back in your calculator here, quit, negative log. It's not ln, it's not natural log, it's just log 0.0066. I'm sorry, so it should be okay, 2.18, which is, yes, it's 2.18. All right, that's for part B. Part C, well, we need to draw the Lewis diagram of HCOOH, which is pretty easy. For carbon and oxygen, you have 2 bonds. To draw the ampere electrons, we connect them. These are all single bond. We make sure like oxygen has 2 bonds, yes, and hydrogen has only 1 bond, and we see carbon has 4 bonds. All right, that's for part C. Part D, we have another equation, chemical equation. It's the ionization of hydrazine, H2NNH2. And since hydrazine is a base, so we have a Kb value of this equation. All right, so it says H2NH2 reacts according to equation above, and we have 40 millimeter sample of 0.05 millimeters of H2NNH2 combined with 50 millimeter sample of 0.25 moles per liter of HCOOH. So we need to write a balanced net ionic equation for the reaction that occurs when H2NNH2 is combined with HCOOH. So we need to combine these two equations first. We have H2NNH2 aqueous plus we have H2O plus, go back to the first slides, we can see the equations like that. So we have our HCOOH aqueous plus H2O liquid, and they should form H2. Okay, let's form H2 and H3 plus aqueous plus OH minus aqueous plus HCOO minus aqueous plus, what we have here, we have H3O plus aqueous. As we know, H3O plus and OH minus combine to form 2 moles of water, and it should cancel with these 2 moles of water in the front. So the net ionic equation is simply H2 and H2 aqueous. I'm going to write faster. Aqueous form H2 and H3 plus aqueous plus HAOO minus aqueous. Okay. So in this resulting solution, is this resulting solution acidic, basic, or neutral? Justify your answer. So so we have Kb for hydrogen here. We also have Ka for H2COH here. We can see Ka is equal to 1.8 times 10 to negative 4 for HCOOH, and Kb is equal to 1.3 times 10 to negative 6 for H2 and H2. So we know this one is greater than the Ka is greater than Kb. What that means? That means since Ka of HCOOH is greater than Kb of H2 and H2, the H3O ions concentration produced is higher than the concentration of H2 from H2 and H2. So the resulting solution is acidic. Right, it's acidic. All right. So last part. Okay, sorry. So we still have 3 parts to finish. We have part E. Part E is strict redox reaction, just very answer. So we know for HACOOH, we know oxygen has to be -2, hydrogen has to be +1. That means we have 2 minus 2, well 2 plus 1, so it's -4 plus 2, which is -2. We need to make sure that the total number is equal to 0, so carbon should have a +2 oxidation number. Whereas for H2, as we know, we have 0 oxidation number. For H, for CO2, oxygen still need to be -2, but so in this case, carbon should be +4. As you can see, hydrogen is reduced from +1 to 0, and carbon is oxidized from +2 to +4. So it is a redox reaction. Because carbon oxidation number increases from +2 to +4, and hydrogen goes from +1 to 0. From +1 to 0. So now we need to go faster. And as you can see, we put the reaction occurs in rigid 4.3 liter vessel at 25 degrees Celsius. And this is the pressure, the graph of the total pressure and times of a gas inside the vessel. So we need to calculate the number of moles of CO2. And you remember this is total pressure. So what that mean? That means the pressure is resulted from both hydrogen and carbon dioxide. So first, we need to calculate the total moles of both hydrogen and carbon dioxide. So let's see, we have PV equal to nRT. So N is equal to PV over RT, which means P is 24 ATM. V is equal to 4.3 liters, and R is, in this case, is ATM, so it's 0.08206 ATM per liter divided by moles times Kelvin times this 25 degrees Celsius, which is 298 Kelvin. The resulted the final answer for the number of moles of total gas is, okay, calculator divided by 6 times 298 is equal to, well, we have two significant figures here, so we need to write 4.2 number of mole. That's for total gas. And in this case, we have 1 mole of H2 and 1 mole of CO2. So number of moles of CO2 is half of the total pressure. So the number of moles of CO2 is equal to 4.2 divided by 2 moles, which is equal to 2.1 mole. So after reactions proceed for several minutes, does the amount of catalyst increase, decrease, or remain the same? Justify your answer. Of course, is remain the same. It remained the same because, why? In a catalytic reaction, you should say a net catalytic reaction, the amount of catalyst is not consumed. You should say catalyst is not consumed. So the net change of its amount is 0. All right, that's it for part 1.